Okay, so it 3.4, it's asking us to find the equivalent resistance seen by the source and find the power developed by the source. So we know the formula for resistance in series and in parallel, right? Resistors in series either goes R1, R2, and resistors in parallel go in this manner. So resistors, so for two, I guess, resistors to be in parallel, um, you would know this. I mean, if you didn't have any idea, you wouldn't know where to start. You could ideally just like go and sum these two and see in parallel and say these are in parallel. And, there's there's two. One thing you want to notice. You don't want to do that. So you know that if two resistors are in parallel, it's because both ends of the resistor, so right, these two ends are the same for both of these resistors, so they share both nodes at each end. So this end for the 10 ohm and the 40 ohm is shared, or the node, and then also this node, right? Erase that. And in series, it only one node is the same. So where let's say we calculate the equivalence of this parallel with this, and we notice, say we have the equivalent, so we might be left with this towards the end, and then it's 18 ohm resistor. You notice that these two resistors only share one node. So let me solve the problem, and yeah. So since these two resistors share these two nodes, we're going to say these are in parallel, right? So I'm just going to redraw sort of. Yeah, so this is going to be our R equivalent one. R equivalent one is 1 over 10 plus 1 over 40, negative 1, right? Oh, 22, 25, 118. Okay, so this should be, let me plug this into my calculator, or actually, for 5 over 40, 40 over 5, 8, I believe. Uh, yeah, just making sure my calculator. Right, all right. Yeah, so it's going to be 8. So then we're going to go ahead and do the same thing again. So then this is going to be equivalent resistance here. And then we notice that these two resistors share only one node. So we're going to assume these are in series. Right? So now I'm just going to, I'm going to try to not redraw it as much. I'm just going to surround them and sort of tell you, right? So 8 plus 22 is 30. I call it equivalent resistance 2 is equal to 30. All right. So then our equivalent resistance 2 this is 30. So I'm just gonna, oops, oh, that's ugly. That's very ugly. I'm gonna 30. 30 is in parallel with 125, right? These nodes are shared by both. So then our formula, I'm gonna write it with green 3. It's gonna be 8 or 1 over 100 plus 1 over 25 plus 1 over 30 to the negative 1 power. And I'm gonna use my calculator for that. So it's gonna be 12, right? 12 ohms. And I'm gonna write the next one in a different color, purple. So now we are left with a simple circuit like this. So part 4, you say, okay, 5 volts. We have this 18 ohm resistor, and now this is our equivalent 3, which is 12. So now we see that these share a node. They don't share each end of the resistor doesn't share the same node. Only one end shares the same node. So then we assume they're in series. Oh, sorry, equivalent resistance total is going to be 18 plus 12, 30 ohms, right? All right, so that's our equivalent resistance. I'm going to rewrite that really quick because it doesn't look pretty. Okay. All right, so the power developed by the source. So we have 3 formulas for power. Power can be I times V squared over R, or I squared times R. So in this case, we have the voltage and we have the equivalent resistance. So power in this scenario would be 25 squared, 25 over 30, which would be 0.83333, if you want to call it. All right. I'm gonna pick up the pace here. So yeah, now that we know what it's in parallel and in series, we know that these two are in parallel, right? Also, along with these 3 are in parallel, right? So we're gonna call that our first equivalent resistance. And I'm gonna switch colors every time just to make it less confusing. I'm gonna do that with my calculator. It's gonna be 3 ohm. All right, so let's go with, right, so this is gonna be, oops, my black. right, so I'm going to do equivalent resistance. So then this first equivalent resistance is in series with the 2,000 ohm resistor and the 5,000 ohm resistor, right? So, well, this 3,000 ohm resistor. So then R equivalent to is the addition. Oh, yeah, which is 10. All right, so and now we see that there is this second equivalent is in parallel with this 10,000 ohm resistor. So do it in blue. So yeah. In other words, this could be 10 over 2, 5,000 ohms. And for the power, I'm gonna separate this. For the power, we have current and resistance. So, 50 milliamps, 50 times 10 to the 3 squared times 5K. So that is going to be 12.5 watts. All right. I'm gonna transition down here. I'm gonna separate this. Wait. It's gonna make more space. Okay. That doesn't, yeah. All right, so here you can either start left or right, it doesn't really matter. You can, the equivalent resistance of this is gonna go in series with the equivalent resistance of this right side. So let's do left to right. Right, so this 900 ohm and 600 ohm is in series. So 1.5K, right? So the 1.5K is parallel to 750 and 500. So I'm gonna do that. So I'm gonna call this the equivalent 1, and I'm gonna, so it's 5K plus 1 over 750 plus 1 over 500. I'm gonna just rewrite that. Which is 250 ohms. And then I'm gonna do this equivalent. So the 1.5K with the 3K ohm resistors are in parallel, and the equivalent of these two is in series with this 2000 ohm resistor. So I'm gonna calculate. So we can do this instead. Actually, we can just do the math here. So over 1. No, I'm gonna make this pretty. I'm gonna make this more legible. I'm sorry, guys. My handwriting's not the best, and it's quite hard to get used to this stylus. I'm gonna do my best. Okay. So the result of this is 3000. So now our circuit kind of looks like this. So it goes, oops. This is sort of what this is our equivalent 1, and this is our equivalent 2. So, right, they only share one node. So they're in series. So 250 plus 3000 are equivalent, our total equivalent for the resistance is 3250 ohms. And the power dissipated should be this formula. No voltage. 65 squared divided by 3250. Use a calculator. It's going to be 1.3 watts. I'm going to move this down. All right, so similar situation with this one. I'm going to do the same thing. So these two right here are in parallel, right? They both ends share the same node. So 1, and then these two are in parallel, plus this resistor that would be in series. So I'm gonna change color for this one, and I'm just gonna call this R equivalent 2. So R equivalent 1 is 1, 1, 3 plus 1, 4, 600 over 4, I believe. Yep. 50. And then R equivalent, oops. R equivalent 2. We can expand this, so it's going to be So it's gonna be this way. It's gonna be so 1/400. Okay. This is gonna result in 171 point. I'm gonna round it off to 0.43 ohms. And now we get a circuit that looks like this. Oops. We would get this circuit would look like this. We have them like this. So we notice, right, the same thing with what happens with resistors in parallel. They share both nodes right here. So then our equivalent total would be 150, right, plus 1/171.43, -1 to the -1. So I used the total value. I didn't really round it off with my calculator, but this R equivalent is approximating 80, or could be, or you can say it's 80. Yeah. Now the power developed here, we have 0.2 amps squared times, I'm going to call this 80. It's going to be 3.2 watts. All right.